Okay, so today is basically going to be a course on graphics fundamentals. For those who I've talked to, you know that we're basically going to try to sum up a full semester's worth of the equivalent of CIS 460, minus all the implementation details and like all of the nitty-gritty graphics inside of that in the course of the following 80 minutes. This is going to be a lot of information. If you guys want to take notes, you're welcome to. If you don't want to, the lectures are online, so you can always go look at this again. This lecture will be shared by myself and by Trung. So Trung, I guess if he's not coming today, he will be either here towards the end of class, but most likely we will bleed over to Thursday because just there's so much to cover and there's no way we're going to finish it all today. Another quick note on class attendance and being here. Someone who is in the class asked me if he could join the class because he went and watched the YouTube thing and saw in the first lecture that I said, I don't care if you come to class on Tuesdays, if you participate in Slack. That doesn't mean never come to class. It means if you have to not be here for some reason 1 or 2 days, that's totally fine. But he asked me if he could just join the class and never come, and I was like, dude, really? Why are you asking me this? So that's not what I meant. Do come, but if I'm not gonna punish you if you don't. Yeah, so I want to get that out of the way. Okay, so broad scope of things we're going to cover today. There's a lot of big words up on the screen, but we're going to try to just take it one step at a time and go very simply through everything. If you've taken 460, there's a couple of you in here, or you know graphics, this is going to be super boring. So, I mean, you're welcome to stay and refresh up, but just understand that it's going to be a little repetitive. So we're going to start with primitives and VBOs, go through scene graphs, transformations, mesh data structures, and that is all and maybe a little bit of animation today. The goal for today is just to get through that first half. And the second half, so lighting and reflection models, virtual cameras, textures, the graphics pipeline, and shaders is what Trung is planning to cover on Thursday. So just kind of whet your appetite a little bit there. Okay, so the first thing. I guess the question here and what I'm trying to get kind of set as a starting point is how do you represent an object on a virtual canvas, right? So if you have, let's say, a phone in real life, this is just my iPhone or whatever, this is comprised of a really complicated piece of what we call in the virtual space geometry that is represented by, either whoever designed this iPhone probably has hundreds of thousands of models of it and planning out every single piece of it so that when they manufacture it, it happens appropriately. You can think of primitives and ignore the term VBO for now. But primitive objects and basic graphics concepts as the building blocks that are going to put those pieces together. So if you wanted to say make a box, so just make what's on the slide right there, a basic cube. That cube will be represented at its lowest level, so purely on the graphics card. You probably won't see this very much in CPU land, as faces, edges, and vertices. So a face is, that diagram is pretty self-explanatory. A face is one flat surface. An edge are the edges of those surfaces, and the vertices are the points which you make edges from. So you kind of build up 2 vertices make an edge, usually 3 edges will make a face. We can talk about triangulation and stuff a little bit later when we get into more advanced graphics concepts. But yeah, so those are the 3 concepts, edges, faces, and vertices that will make a mesh. I'm going to use the term mesh all the time, so that's what a mesh is if you heard me mention it when we were decomposing VR stuff last week. So we just showed a box, but a box isn't enough to make a graphical object with, right? So most VR application or most graphics applications will give you a set of what are called primitives. So primitives are essentially saved sets of faces, vertices, and edges that comprise these images that you see on the screen. So there's a sphere, there's a torus, there's a cylinder, there's a cone, there's a tetrahedron or something like that, and there's a couple planes. You can think of a primitive as an assembly of these vertices, essentially it's just the vertices, in such a way that the positions are all relative to an origin. So saying, all of these primitives are saying is we know that if you put 8 vertices, each 1 unit away from the center point of a sphere, you're going to have a sphere. That would be a really rough, you would have not that many faces and it wouldn't look very good. But I think a good articulation of what these faces and stuff comprise and how adding more faces, vertices, and edges will add more detail to your objects is the difference between these 2. So you could argue that both of those are rudimentary implementations of a sphere, but you can see that the one on the left has way more detail in the mesh, which obviously makes it look better, but is more expensive to the computer. So yeah. Does anybody have any questions on primitives or meshes? Is any of this confusing? No? Okay, that's good. So we're going to move on. So someone may ask the question, how do you get from a sphere to like this guy? And that's a huge gap, right? So like, how do you get from, you were just playing around with like little boxes, like, woo, we're in fun graphics land. And now you have like this character that has been sold for like 10 years and makes millions of dollars in video games. The kind of bridging point there is understanding how you can build and assemble these meshes together or these primitives together to make more complicated meshes. So who can tell me from this screen right here, what of these objects, or what do you think you could combine and put together to make like these tassels, or like these pieces of cloth? Anyone? No? A plane? Did I hear a plane? Exactly. So if you think about it, this little cloth, although it has some wind-based deformation on it, is essentially just, do I have a cursor? Is essentially just this plane like shrunk and bent a little bit, to use very rudimentary adjectives and verbs. But what you can think about is that every piece of geometry you see on the screen is just, use the basic building blocks, mash them together, move around the vertices and edges, and combine them until you get something more advanced looking. So anybody who's remotely done anything with graphics has probably heard of Maya or Blender. Those are like two big graphical engines that let you kind of combine these primitives and objects and curves and all this stuff together from an artist's perspective mainly. So those programs will allow you to do all of this kind of math in the background, but not actually know the math you're doing and just kind of point and click and drag stuff and move them together. So they're really powerful programs. At the end of today, I'm going to hope to jump into Maya, use it to visualize a couple of the concepts that we're going through. But yeah, so the last point on there is, I really just put that on there to confuse you. Non-uniform rational B-splines. If anyone has any remote idea why they made it name something so complicated, please tell me. But the basic concept is a lot of these surfaces are not very easily created from non-organic objects, right? So everything that you see here looks like it could be man-made, and probably would be man-made if it was made in real life. But when you go from something like that to, say, like a leaf, I mean, the cloth on this character's front is a good example, if I can find some chalk, of something that is not necessarily a normal polygon or something that has flat edges everywhere. So there's a technique called splining, and non-uniform rational B-splines are a subset of splining, where you can take three points, and instead of connecting them like this and having a jagged edge, you can use those points to interpolate a distance between them and make a curve like that. So that's what a spline is. I'm not really describing exactly how you would do this, but it's not that important for anything to do with VR because you're never going to have to write this yourself. It's like the foundation of every graphics library. But essentially what you can imagine it doing is taking little points along and you essentially split line segments over and over and over again, and it's almost like a limit. You just split them over and over, and then you generate the curve as you split them, and that'll make a smooth surface instead of a jagged surface. That was super top level, not at all rooted in any real implementation, but at least you can see where a spline comes from and where you could get something like this curvature, for example. Does that make sense? Does that confuse anyone?
So the green B-spline, is that Bezier?
Yeah, I think. Who would know this? Helen, do you know? I don't think it's a Bezier. Yeah. No? I think it's just a B-spline, yeah. It could be binary, but I don't know what the B comes from. But yeah, we can. If I show you them in Maya afterwards, it'll look I feel like it'll sink in a little better. But we're going to get there in a second. So any other questions on NURBS, polygons, meshes? No? Okay. Moving on. So we've talked about what the data that goes into a mesh is, but we haven't really talked about what a computer will do with that. So later today and probably on Thursday, Trung will be talking about what a GPU does with that data and how the GPU will actually turn those like literally just vectors into graphics on your screen. But at the lowest level, you have to think about those three components of edges, faces, and vertices are necessary to actually physically draw or see the object in real life. And so whatever you do with the meshes and the objects in your scene at a high level, so in your graphics engine, in your game engine, in 3JS or in C++, whatever it is, at its lowest level, VBOs, so vertex buffer objects, are used to pass those data, that data, essentially in a linear data structure, usually a C++ vector, directly to the GPU. And regardless of how you store them, if it's a tree, if it's like a KD tree, red, black tree, whatever, at its lowest level, you're going to need that data in some kind of linear fashion so your GPU can understand. And that brings us to like the next big divide here, which is saying everyone who's taken 371 or 380 knows what a CPU does and like how it interacts with your computer, but the GPU is a completely different processing unit. So you have to think about the division between CPU and GPU is like literally having a line in the sand between two regions of your computer. You have to marshal data between. So has everyone heard the term marshalling? Is that new? Yes? No? Yes. Okay, there's one yes. So marshalling data is essentially saying we have these bits of zeros and ones. We have to figure out a protocol to translate them between source and destination without actually like doing you want to do the minimum amount of work possible to change the zeros and ones so that both sides can understand it. Does that make sense? Because like the bigger your zeros and ones are, the more you don't want to have your work be linearly tied to how big the data is. So when you marshal it, you want to set some kind of protocol and so on. But yeah, anyway, so what I was getting to with that was that your CPU has to pass everything that you do on your computer to the GPU in some fashion. That's done with VBOs. If you want to learn more about how this stuff works or like how the DMA, which is direct memory access, works between the CPU and GPU, take 460 or ask me later because it's not super relevant to the implementation that we're talking about today. Moving on, so we've talked about how you build objects. And so on this little silly diagram that Adam Malley wonderfully made, if you guys don't know Adam, he's the greatest. Say this was a sphere and these were two like rectangular prisms. We've talked about how you assemble those objects, but we haven't talked about how you move them, how they relate to each other, how they have position, how they have meaning in the context of your virtual world. So the basic idea here is that a scene graph is essentially a tree. Everyone has seen a tree. That lets you store not only the mesh information, but other attributes about them, those meshes, in a way that you can derive positional information and rotational information and scale information relative not only to that object and not only to the entire world, but to the parent objects and anything else in its hierarchy. So what is a hierarchy? What does all of this mean? It's pretty aptly visualized on the screen right here. But you can think about it as objects can derive from, well, basically every object in your scene has to have a parent. So what is a parent? A parent is just basically a frame of reference. So an allegory to the way a scene graph's parent and hierarchical transformation process works is if you've taken Math 240 and you've seen anything to do with a basis. So a basis vector defines, I forget what the math term is, but it basically defines a span. I don't know if that was the right, can someone check me on that? Like, is that the right math term? It basically defines a way to perceive the world that you're talking about. So you can think of a scene graph as essentially a tiered set of bases where the first point is just like the origin of your world. So the center of the virtual world is going to have a point 0, 0, 0. And if I have an object that's like 5 units high, that object's translation, so its position, is going to be 5 on one axis and then 0, 0 on the other two. But that 5, 0, 0 is relative to the root of the scene. Whereas if I had a second object, so what's the thing here? So root node. This world has an origin of 0, 0, 0, a rotation of 0, 0, 0, and a scale of 1, 1, 1. That means that there's no modification to it. This body node would be this blue thing right here, so pointing to right there. And that's saying we have a sphere. This is in 2D, so ignore the 2D part. It's just because there's no 3D image. we have a sphere that's located at 0, 0, 0, translate, rotated 0, 0, 0, but scaled 2, 5, 2, so, or 2, yeah, it's scaled. So basically what that's saying is anything that inherits from that sphere, from the body, will also inherit the properties of this sphere. So if you have arms, arm node R and arm node L, not only will these arm nodes have their own translate, rotate, scale, but that's compounded with the parent to create what's called the global referenced transformation. So does that kind of hierarchical sense make, was that clear? I know it's like maybe a little bit confusing if you haven't seen it before.
So if you have like multiple of these little guys, they would all be related to like their own kind of root node point that you would then place them somewhere that those like root nodes would relate.
Yes.
They'd be like added as children to the.
Exactly. So a good way to think of this is like the root scene node that is at the top of the slide is virtual. Like there is no real root scene node. Anything that doesn't have a parent is just going to be defaulted to being a child of the root. So you could have as many of these little like stick figure guys as you want that would all derive from the root, but since the root has no transformation properties, it's like virtual. It's like a 0. It doesn't really exist. Any other questions on this slide? We're going to go through an example that should hopefully make this a little more clear, but I want to be sure that like the concept of the hierarchy is clear before we move on. No? Okay. So if you have a tree that has all this information, so you have like a root, and node 1, node 2, node 3, so on. It's not a binary tree. Don't think of it as one. The question is, if you have that data structure stored in your code, how do you actually traverse it to generate that, what we were talking about, basically stack-based transformation? And the answer to that is a normal post-order traversal, explore all children before exploring parent. That makes natural sense, right? Because if you think about it, if you wanted to know where this arm is positioned from just the perspective of this node, you wouldn't have all of the information like you would need to actually put it somewhere in the world, because you have to go to its parent, and then its parent, and so on. So by doing a post-order traversal, essentially what we're going to do is eliminate one row of the, well, not one row, we're going to essentially bubble up the tree, so your recursion stack will be its largest on your way down. So you like, explore node, has children, okay, put on stack, go to children, put on stack, go to children, all the way to the bottom. But then if you think about it, when you're actually calculating the properties for each object in your transformation tree, every time you calculate one and move up a node, move up a level, like a height in the tree, you can pop off the other stuff because you're done with it. So does that make sense? If you're doing this in post order, you can essentially throw away the extra memory, and it's like the most memory efficient way to do it because you don't keep excess stuff in memory when you're going through. That's really important that we like note that, because if you did this any other way, it would be like super inefficient and no bueno for your processor. And yeah, so the code on the right is like a pseudocode example that's like from Sublime, if anyone recognizes the color scheme. And yeah. Okay, so we're going to try to go through an example here and kind of visualize exactly what we just talked about. So if your like scene graph rendering algorithm, let's say, was starting to render your scene and like drawing the objects on screen, you'd start at the green highlighted node at the top, and then you just essentially go down. So the thing on the right is the recursion stack, and the image on the left is like whatever is green is what's, you can imagine the program counter is there. So we're going to go down, and once you get to a scene graph node entry that has a geometry pointer and doesn't have children, you can draw it. So you're going to start with this normal undeformed cube, and then you're going to end up with the elongated and skewed rectangular thing on the right. You can see that's done by just, going through body into arm and so on. Next, go to the next child, do the same thing. It's just mirrored. Pop back up, draw the parent, and then, yeah, that's about it. So that was just a really brief visualization of what I just said. Was that confusing? Did that make sense to everyone? Okay. Please understand, the more feedback you guys can give me, the better, because I haven't like taught this or learned this for a couple of years, and it's always hard to gauge where someone else is coming from if they don't have the same background. So please help me out here. Like, give me some feedback. Let's make this interactive. Okay, so I don't know how much detail we need here, but this is essentially, these next few slides are going to show in what order specifically you apply each, let's say, transformation, and why that order matters. So we've talked about the fact that you bubble up this scene graph, right? So you start at the children and go all the way up to the top to be all children before their parents. But how do you actually take the data that's stored in those transformations and mathematically get the right answer? So the answer to that is essentially you always follow the same TRS pattern. So if you heard me referencing TRS when we were doing like the VR app dissection last week, translation, rotation, scale. And so what is basically said on the slide is that you always have to apply those in the same fashion, and I'll show you why. So I'm going to draw some like basic matrices on the board, and then we'll see in the future slides how those play into the actual representations. So I'm going to advance this one. Okay, so he was doing translation first and then going to scale. So remember, we're going in order of TRS geometry. So, okay, who has taken a graphics class can tell me how you represent a translation, a rotation, or a scale in a matrix. There's a couple of you in this room, and you guys better know this. Ellen, Carolina, Davin. Okay, one of you.
So I use like a homogeneous matrix.
Okay,
It's
great.
like a 4x4 matrix where the top left 3x3 represents rotation. On the x, y, and z axes, which are represented in the columns, and then the last column is the translation.
Okay.
And the one on the bottom, well, is essentially just makes rotation.
Right. So that was great. I wasn't expecting you to know like the rotation ones because they're always like hard to remember. But the key point I wanted to explain here is that what your computer is doing under the hood when it's doing these transformations, if you've taken Math 240, you've seen this, is essentially using a four-dimensional matrix to represent a three-dimensional transformation. The fourth dimension, which is important that Ellen noted, is because the reason you need these four dimensions is to maintain what's called homogeneity, or I think that's the right noun for homogeneous. But anyway, if you concatenate these, you need to be able to kind of unwind what you did, and you need them to always concatenate in the right way so that you preserve that state. So the reason this fourth dimension is there is because you basically will use the extra rows and columns to multiply these so that if you stack them, they stack correctly. I'm not going to explain them. Like, you can derive the formula for why that works on your own time if you want to. But the basic concept here is that, so you keep this, like this one basically is like the identity column for that. Well, it's like, if you had an identity matrix, that would be one. And then what Ellen was saying was a great example of these last three rows are used, last index of the first three rows is used to do translation. You'll see sines and cosines up here to do rotation, but we're not going to talk specifically about how you do those because the game engine won't do it all for you and you have to do no math. So doing no math is good. If your computer can do it, let it do it. But the idea here is that if you put like 5 of these matrices next to each other and always maintain the order of applying translation, rotation, and scale in that order consecutively, you will always end up at the same result given like the same graph. So you just maintain that one-to-one relationship. So yeah, first slide, we look at this bottom node, so the green node highlighted. Then we take the scale from the second one, and you can, I'm not going to go too much into detail here, but you can see the image on the right will change as we kind of perform these operations. So rotation, translation, so on. Yeah. So what I want to do is, because I feel like we've talked this to death a little bit, I'm going to put the actual slides for this, not only the recording up, and then if you want to go through this on your own time and write it out on paper, I highly recommend you do that because there is a homework that we're giving out at the end of today that will ask you to do this. So I want to make these slides available as like a given base example. Okay, so before we move on to mesh data structures, does anyone have any questions? TRS, we're going to be using those terms all the time.
Wait, so can you go back to the scene graph?
Which one?
Yeah, this So all the TRS transformation that's being done to the like in node 2 is also being applied to node 3.
Yeah. Yes, exactly. But you have to bubble up from the bottom. So does that make sense? Because if you didn't,
do the ones down there first. And
yes,
up to the top.
yes. Because if you did it in the other direction, and you like the what's the term? Matrix multiplication isn't always commutative. So if you do AB, is not the same as BA. That's the reason. Yeah. So any other questions before we go on to mesh data structures? No. Okay, so the question now is, we have this basic way of storing mesh information, and we have a way to correlate these meshes from one to another and essentially understand how they live in the virtual world. But how do we actually store this information so that when we want to do stuff to our scene or to the virtual world, we can do it efficiently and not kill the computer on clock cycles? So yeah, that's pretty self-explanatory. So how do we do that fast and efficiently? So what we're going to do now is go through, if you've, again, taken graphics classes, repetitive, we're going to go through 4 or 5 data structures that is used to store this information and talk about each one, where it's useful, pitfalls, benefits, and so on. So the first one is called a half-edge data structure. Now, we've talked a lot about faces, vertices, and edges. What this drawing is essentially representing each edge as 2 half-edges, hence half-edge. And essentially those half-edges are vectors that point from a source to a destination vertex. So you have like essentially vertex A and vertex B, and 2 half edges together, stacked on each other, comprise 1 full edge. So the benefit here is that if you have the highlighted red half edge that's on this bottom face, not only do you know where the source and destination vertices are, but you also have the next half edge. You don't always store the previous one is drawn on here, but that's only for the sake of drawing on the screen. If you were writing this, you would only store a pointer to the next half edge. But so say you wanted to do something like, let's say, explore every face on an object. Who can think of why having this half edge data structure would be better than just like iterating through a list of edges of like normal non-half full edges?
Because I'm guessing because you can go through the half edges like a linked list and just go through it in an order.
Exactly.
To go through different faces instead of just iterating through all the edges, which might not be in order.
Perfect. That's a great explanation. So say your renderer, so the thing that actually draws these virtual objects on screen, says, okay, I can see this phone from where my camera is positioned. Now, all I have is a pointer to like the root half edge of this phone. If I wanted to find out the full space to which like it encompasses, and you have to think of this from a computer's perspective, right? The computer doesn't have eyes; it just knows like something is there. You can essentially follow a half edge loop all the way around. And so say you start here, so you go like that, until you get back to your source. And once you've done a full loop, you know you have a face. Does that make sense? Yeah. Okay. So the benefit is you can find those faces pretty quick. But say I had another face right here that I can't draw, so don't expect me to be very good at it. But say you have another face right here. Not only can you circle and ring around your first face, but you can flip onto the opposite half edge. So say you're going from the red one to the black one above it right there, and loop around the next face. Instead of having to go like do a linear scan through the entire like edge array and find the next face you're looking for. Does that make sense? Okay.
How does the flip work? Like, you just mentioned that every like 2 half edges compose with like an edge, but like how do we know specifically like that edge has like you can flip it over?
Right, that's a good question. So in the purely like theoretical sense, the 2 half edges comprise an edge, but in like the code sense, you would have like basically just one pointer to the first half edge, and a half edge struct would have like next, opposite, face, and you could occasionally have previous and start and dest. So the half edge structure, I overloaded this. This is not like the minimal implementation of a half edge, but this makes it, like if you're okay with sacrificing a little bit of space, makes it way faster. You'd have pointer to the next one, you'd have the flipped opposite one, and then the face and your source and destination vertices. So that's what like the struct would be. Does that make sense?
Yes, but I still don't see how you know that you can flip it over.
So
You have like, so wouldn't that edge then would have like 4 half edges or something? Like you have 2 different edges, one on this face and the other one on the other face?
no, so this edge on the drawing right here is comprised of these 2 half edges. So one pointing that way and one pointing that way. This is like, I'm blazing through this and this is a really confusing topic, so if this is at all confusing, please do not like hesitate to ask questions. So does that make sense?
I guess, yeah.
Okay, maybe it's,
So like every edge in this like octagon or like hexagon has a half edge, like an opposite one. But then if you try to follow this opposite one, you would see there's like more connected half edges, so there's another face.
exactly.
Whereas like the others don't have, the opposite ones don't have like other connecting ones.
Right. So I drew as part of it. This would be like a improper mesh because it would be open, right? Like you would essentially, if this was like well, I'm not going to go all the way back, but if this was the primitive that was like all those octagons like making a sphere, then essentially every edge would have to have an opposite. Because otherwise, if you have a half edge without an opposite edge, you have a hole in your mesh, right? Because this would just be a gap. So there should theoretically always, like, unless you have an open mesh, which is very like unlikely, you should always have an opposite edge. And that's the way you can traverse the mesh itself. Did you have a question? No?
Yeah.
Yeah? Yeah, oh, okay.
So each edge can only be associated with one face. Like it's not possible for an edge to
Yes. So exactly, that's the key point here, is that each half edge can only have one face pointer because it's the face that's on the same side that edge is on. You have to think about like the edges. If there was like a real edge and it was like the peak of a mountain, you have one edge here, 2 half edges on either side, like one half edge doesn't know anything about the other one's face pointer, right? It only knows that it's on one face.
What if you were trying to make like a book
Mm-hmm.
that was all the pages connected to one point?
Okay.
And they're all faces.
Okay.
Like, how would they be in pairs, or would they all like know about each other?
Good question. So I'm going to draw a perspective of like the spine of the book. And then you can imagine this going on. Say there's like a binding right here. And then this is the rest of it. So you have to think of like each page wouldn't be like there is 2, it would be like a box with really, really thin on one dimension. So it would look more like that. Does that make sense? And then
It makes sense like that, but like, can there be more than like 2 half faces? I mean, like half edges, like in one edge.
no. So the way you could do that is if you put a vertex in the middle here, you would split this into 4. So if you put a vertex right here, you would have 2 half edges here and 2 half edges. So you can add vertices. Like basically every time you add a vertex to an edge, you have to split that into 4 from 2 to 4 half edges. Is there a question in the back? Yeah.
What did you mean by the start and destination, or in your struct?
Oh, the vertex that it emits from and the vertex that it ends in. But again, this is not the minimal implementation of a half edge. Like there's ways to make this more space efficient, but like who cares about space at some degree if it's faster computationally. Sure.
So just for like a better understanding, we could just get like start and end from next and opposite, right?
Yeah,
Like,
so
from next and previous.
you really only need one vertex. You don't need the source because you could just follow the loop around until you get a half edge that is the same one. and then the previous one would, you could generate that information computationally is my point. Okay, I think, so we've talked about all this, but yeah. Next data structure. Everyone who has taken, I think 120, does 120 do quadtrees? Is that a thing? If I remember that right. Okay, so if a quadtree represents two-dimensional space, an octree represents three-dimensional space. And the way you can think about an octree is essentially dividing the world into octants. So you start with that cube, break down into 8 smaller cubes, and each time you enter a new level of the octree, you're creating 8 more of whatever thing you just divided. Hence oct 8, yeah. So what would you use this divided space for? So one thing we haven't talked about yet that, again, bear with me, we're going to get to it eventually, is the concept of rendering. So actually drawing these virtual objects on the screen. And that can be a really, 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 really slow process. And the goal is to make that as fast as possible, because if it's too slow, your frames won't be ready in time. So the frames are what the user sees. And if the frames don't come to the head-mounted display fast enough, you're going to be like Ed and end up in a bad situation, in a bad, you're going to get motion sickness. Yeah, that's not good. So you want frames as fast as possible, which means you want your renderer to work as fast as possible, which means your renderer has to be able to find objects in the scene as fast as possible. So it's all about speed. So what an octree does is let you say, okay, say my camera that I have in the virtual world can only see this cube. Then I only need to go into the octree and find all of the meshes that exist in that cube, and I can ignore the rest of them. So simple tree traversal, go through the tree, iterate, go through its children, so on. Does the concept of an octree, was that clear? Does that make sense so far? Yeah? Okay. So we've talked about why binary disk partitioning is useful. We've talked about why it's effective, but what's a bad thing? Who can think of one situation where this would be utterly horrible? Anyone? This is a little bit of a reach. I just wanted to share.
When you move around, you're not pre-processing anything, so it used to render everything that's new in the view.
True. So I'm not sure exactly what you mean, but do you mean if the scene changes, you have to recompute this? Right. So if you move an object, you have to put it into the next octant or whatnot. That's definitely a cost. That may not be the worst pitfall, but that's a good one. Anybody else? Ninja?
So is this structure storing a mesh of an object, or is it talking about space?
It's just, it stores pointers to the meshes that exist in those octants.
Oh, okay.
Yeah. So kind of going off of that, what happens if I have an octant that has 100,000 meshes in it, and then I have 7 other octants that have nothing? My tree is useless, because essentially your runtime for scanning through that last octant would just go to linear scan anyway. So just like any other tree, it's not, well, not like every tree. This is not a self-balancing tree, so you can overload one side of it very easily. And if you do that, you're back to O of n to scan through all the meshes. Very, normal computer science data structure stuff. Okay, so next topic. BSP. So, okay, is anyone here a gamer? Have you ever seen the term BSP used in a game? It's a lot of old school stuff has it. Okay, so if you haven't seen binary space partitioning described in a game before, you're pretty lucky, because the last time BSP was really used effectively was in Doom, and that was in the early 90s, I believe. Anyway. So to illustrate the concept of what a BSP tree is, if you take this, again, everything on the screen right now is in 2 dimensions. You can imagine it generalized to 3, but it's harder to visualize 3 on a PowerPoint, so we're using 2. But, so if you have this, this room with all these dots being meshes, what a BSP allows you to do is basically create a binary partition in the space every time you want to segment your meshes out better. So what we were talking about is a pitfall of the octree, where if you have every mesh in one octant, with a BSP, what you can do is, at will, divide a space into 2, so hence binary space partitioning, and essentially create new spaces. And here's the trick: they don't have to at all be even in area or volume. It's totally up to you. So you end up with really disgusting line. Who wants to go through that and figure out positions? Anyway, that is not ideal. But BSPs were a really great hack for games that had to basically load everything into like 64K of RAM. Like, can you imagine that? Like, you're putting an entire game into 64 kilobytes of RAM is like nothing. So the advantage of a BSP is it's super space efficient. It just is computationally like a huge pain in the ass. Like, you never ever want to work with this if you don't have to. I can't reiterate that enough. But at the time, it was super useful. So the benefit here is that these BSPs don't have the same overloading problem as octrees because you can just subdivide the space as much as you want. Does that make sense? Okay. All right, so next data structure is a BVH, a bounding volume hierarchy. So similar to a BSP, a bounding volume hierarchy allows you to make groups of objects in a scene and kind of group them effectively based on certain properties, where they're located, whatever. The benefit of a BVH over a BSP is that a bounding volume hierarchy doesn't have like these messy like divided line segments that are splitting up space. Essentially, you can just you can imagine just drawing a box around objects that look close together, and then as those boxes get overloaded, you split them into smaller boxes that contain fewer things. So who can think about like why, this is again a reach question, but why would a BVH be better to work with than a BSP?
The boxes are more easier to do the math with because they are like a square or like a rectangle, so it's easier to
Sure.
calculate.
Okay, what else though? Like how, if you have a, how do I phrase this? So say we go back to the BVH or BSP implementation. Say I wanted to go from the purple dot to the yellow dot. Like how would I mean, it's like mess, right? You have to like navigate the line segments until you find the right containing volume, right? But with the BVH, you have more of this like tree structure. So you can kind of go, and you know that if it's not in your child tree, then you pop up, go to, does that make sense? Like it's instead of like randomly bouncing or scanning through these line segments, you can just follow the tree structure and go to where you need to go. Was that clearer than the BSP? Yeah? No? Okay. Well, hoping that was tacit approval. And yeah, so that's a BVH. So basically what we just did was cover like all of the, in a sense, like basic data structures that you use in graphics. You may be asking, like, this is a VR class, like what the hell does this have to do with VR? That's a very good question, and essentially the reason we're going through all of this is so that when you work with Three.js or when you work with Unreal, when you work with whatever game engine you're working with, you have to think about the fact that the renderer and all of the code under the hood that you don't have to touch is doing all of this for you, with the hopes that whatever you're telling it to do on top of those lower level functions, you can optimize for the fact that it's probably using a BVH somewhere. Like its renderer is probably going to render things like that. Now that may not be an issue for you, but if it is, it's good to know that that's what's happening so that you don't like run into a wall of debugging and say like, why is this so slow? Why is this not working? Right? And yeah, but you also have to remember that every data structure that we've just talked about is just like a big giant list of pointers. So all of the actual like object and like memory-based data will be still stored linearly in a VBO somewhere. So the great news is that these data structures, more likely than not, are not going to hold extra memory for you and will just be like tons and tons of 8-byte pointers. You can like navigate them, use C to your advantage, and so on. So before we transition into a whole different realm of graphics, does anyone have any questions about scenes, about VBOs, about meshes, about data structures? No? Okay. All right. So moving on to the fun stuff. People always ask, so we've talked about today, and people always ask, you have like these static objects on the screen, like what good is that? Like what am I going to do with a screen full of boxes? How do you move them around? How do you make them interact? How do you make this an actual experience more than just staring at a painting? So the answer to that is through, there's a term called animation. Animation is essentially varying the properties that we've talked about of objects to create motions. And the way you can think about that is really the more you boil down into graphics, you're essentially making like the screen is drawing something once every fraction of a second. So if you change things between those fraction of a second drawn images, you can create the appearance of motion. And that's the crux of it, right? So say I have this an object is moving along this path, right? So it's like either going that direction or this direction. If I wanted to, quote, animate this object, say this thing, all you would have to do is modify its translation property on some certain time interval so that it moves a certain distance between frames. And then as those frames compound together and you're running at 60, 90 frames per second, it will have the appearance of motion. So that's like the core fundamental concept of animation. And we talked earlier today about a spline, so I drew those 3 points and like talked nerves and all of that stuff. If you think about it, it could look really, really, really bad if you just move an object a constant or non-constant rate per frame. Because you could end up, say I want to get from point here, from A to B. Say I just did something where I've like moved, I don't know, say it just pushes like 10 pixels a frame, and the frame rate isn't very good, so the user can actually like detect the difference between frames. You could end up with something like this. Like that wouldn't look very good. That wouldn't look like natural motion. You would have a really hard time like not saying like this is a horrible game, animation experience, whatever. So we've talked a lot about splines and making these curves, and like little kind of industry tip here, the secret to like what Pixar and well, to some extent Disney, but mainly Pixar do towards making their movies look good is they think about like what does an actual person do when they're moving, right? So I'm not like an automaton moving like this when I walk. Like every frame is the exact same, my knee always goes at the same height, whatever. So there's certain like inherent physically driven lags and time changes that are representable using splines. So like in Pixar movies, what's a good example? So like when Buzz Lightyear does his like jumps, right? He has like superhuman abilities in his spacesuit or whatever. If he jumps off of a platform from like here to over there, they're gonna do some spline-based motion to exaggerate his jump, quote, jump animation so that like he squats down really, really slowly and then explodes in that direction very fast. So like the way you spline this motion is what will essentially give realism to everything you're moving in the virtual world so that the user can like think of it as reality. So it's really important if you think about the way those splines work with, especially with human motion. So going on to human motion, this is a really advanced topic, so we're gonna just try to cover the basics of it. But it's very easy to imagine how you would move like a sphere along this. Say I wanted to get like this remote from here to where my other hand is. It would be very easy to just take this remotes object and move it like that. Simple translation, just move the root object. Don't worry about anything else, right? But what about more complicated things? Like me walking is a lot more of a complicated motion, right? I'm moving different muscles in my legs, my upper body is turning slightly side to side, right? There are all these different, essentially, subconscious animations and subconscious motions that you have to think about representing in the virtual world. So that's handled through a process called skinning. So skins use the concept of a rig. Now in this image, I think this is from Maya, maybe 3D Studio. But you can think of a rig as the underlying representation of a person or a creature's skeleton. So my skin is a skin. Everything I do in the if I was representing myself in the virtual world would be done by moving my skeleton, and so moving like a bone that represents like my shin or something up a certain distance, and then the same way like in the real world, like I can't move my shin out of my leg, right? So the rest of my leg moves with it. And so that process is called skinning, which is where you attach a mesh, so what we've just talked about, to a rig, and then every time you move something in the rig, you, quote, deform or change the mesh. Was that clear? We're going to talk a little bit about how this works, but I want to make sure that the concept of rigs and meshes and skins sets in. Okay. So if you've ever been in the SIG lab, there's a big set of really expensive looking cameras on the ceiling-ish area, like top of the room. Those are motion capture cameras, and essentially, whenever you see someone like walking around, you look a little bit like a goofball in like the suit with all the little buttons on you, and like anyway, look like a tightrope walker or something. Those basically dots on the physical human, so like on me for example, are translated into a rig, which is then used to deform a virtual mesh in 3D space. That's the way motion capture works. So, this we just talked about. One question here is like, so you have this representation of a skeleton, right? But how do you actually calculate how far each point on this mesh has to move when you move the underlying bone or the underlying joint? And you also have to think about those joints can't have like infinite rotations, right? Like I can't spin my arm farther than that. You have to think about how those joints can inspire physical restrictions on each other so that when your character is moving, or say you have an AI controlling that character, the character can't like break its arm backwards. So there's a lot of math. It's all physics and literally 3D math that goes into representing the way these rigs control the meshes that they're skinned to, or the vice versa. And yeah, so it's the basic concept there. We're not going to talk too much about what each algorithm does and how this is calculated. I did just want to give a little shout out here because there's a concept called dual quaternion skinning, and we haven't really talked about what a quaternion is, but now is as good a time as any. That was invented by a Penn professor who unfortunately left, but it was awesome because like he was here and he was one of the people who was the foundation of the way you see this motion enacted in games and movies. So yay, Ladislav. But yeah, so before I talk about quaternions, the other kind of algorithms that are used and that are going to be happening in Unreal and Maya and everything else used under the hood are either linearly blended skinning or heat map diffusion-based skinning. So you can imagine if you were just going out of the box and implementing something like this, right? If you have your task would basically be if you have point A and there is a little bit of mesh skin around it with like vertices here, here, here. Say I move point A over here to point B. Your task would be to determine how far do all of these vertices have to move based on that motion. So a kind of naive approach to doing this would be linearly blended skinning. And that's kind of thinking about, if you have so for each vertex on that mesh, it's actually visualized very well here. There's like a little red dot right there, that's the bone I have selected, or the joint. And those yellow and red areas are the different vertices of the mesh that will move, and to what degree they will move if I move that joint. So linearly blended just means that you take a linear coefficient and apply it so that the further away the mesh point is from point B or point A, you move it accordingly. So quite simple. Heat map diffusion is like a theoretical thing, but essentially what you would do is you would imagine that you expanded like a thermal equation, or you imagine there was heat emanating from that joint. The highest points of where that heat diffuses to on the mesh are moved the most, and what the colder, farther away, so on. I'm not going to talk about that because it's like a little ridiculous to think about implementing, but real quickly, a quaternion is a unit of, well, it's like a mathematical structure used to represent rotations. There's a real and an imaginary component. It's really, really, really complicated math. I don't really want to talk about it too much. If you guys really want to talk about it, we can talk about it in office hours. But just know that there's a concept called dual quaternion skinning that alleviates some of the problems of linearly blended skinning. So as a kind of point of explanation here, who can imagine a problem with like this linearly blended approach? Anyone? I like completely off the wall here. Okay, so I'll draw an example and you have to tell me what happens here. So say this is a person and they have their arm kind of like bent inwards like this. And I have a joint here for the shoulder. That's like, this is an imaginary person. Again, my drawing, I'm sorry. But this joint right here, what happens to this point? Like that point on the mesh is pretty close to that joint, right? So like if I move my shoulder up, you could actually get something like this joint would move up with it and end over there, just because it's close to that joint. So you could like, another good example is if my hand was here, everyone see, okay. If my hand was here and I move my hand out, and I use linearly blended skinning, I could like pull half of my leg out of my leg, right? Like you wouldn't want that to happen. So that's a pitfall of linearly blended skinning that dual quaternion skinning avoids. Yeah, any questions on skinning? This is, again, really like advanced stuff. The one thing I want to caveat here is like not only will a lot of stuff we covered today be on the homework that's given out today, but if you're ever doing anything in VR or in graphics in general with a person, you will see skinning and you will see joints. Odds are you're not going to have to rig something by hand because like that's really hard. You don't want to do that. It's a waste of your time, especially in this class when we don't have that much of it. But you will have to see how this happens, and you will likely be animating people. So this is really important to understand like how this plays into everything. Yeah, so kind of reiterating this, these are hard problems. All the game engines will do this stuff for you. There's no like drop down for linearly blended. Actually, there may be, but you shouldn't touch it. Just let the engine do its thing, but it's important to understand how this stuff works so that when you're interacting with it, it's not like a total black box. Yeah, so we have a little bit more time. I think there's 20 minutes where Trung can start his section of this, but graphics homework is due next Tuesday. Really quickly, I'm actually going to pull that up right now, and we'll just show you what it is real quick. So this is on Google Drive. It's linked. The course website has been updated. And so pretty basic stuff, like you basically do a transformation by hand like we just talked about, more transformation things. Some of these questions at the end you may not be able to answer if we don't get through the content today, but we'll get to it on Thursday, if not today. You'll notice there's one on animation and skinning at the end. That's why I referenced it. And yeah, so that's that. Any questions on what I have done so far? Anything we've done today before we move on to Trung's section on rendering and other things? No? Nothing. Does anyone want to see this in Maya? Like, would that be helpful if I parented some stuff and moved it around? Yeah? Yes? Okay. That's what I thought. So this may be more useful than me talking about it. Okay, so as I said, Maya is a graphical toolkit. All the stuff I'm going to be doing on the screen, you can also do in Unreal Engine and 3JS, but I feel like it's just a little bit easier to demo it when I do it right here. So these buttons at the top are basically the primitives we were talking about. Translation, so the T component is as simple as moving one of these arrows. You'll see that if I can bring up the attribute editor. There, so TRS. As I move this thing, it's moving relative to the root of the scene. There's no children attached to it. It's just its own fully functioning object. I can rotate it. I can scale it, and so on. So if I make a different object, and then I move it, and then I think, okay, so I've selected both of those. I think it's just P, but I'm looking for the, so if I hit P, it should have, yeah, so it parented. Now this object, you'll notice that when I select the box, it also selects the cone. So I push P on my keyboard, that's parent. Sorry, I didn't know where the menu item was. But you'll notice that like this transformation acts, okay, so first of all, Maya puts these arrows at the local object's origin. So the 0 point that's modifying this cone is the origin of the transformation of the box. So when I move the box, it will move both of them, but relative to the box. Now if I can bring up the hypergraph. So you'll see that if I select just the, just the cone, first of all, that cone has its own transformation, rotation, and scale properties that are relative to the origin of this. and not to the 0, 0, 0 point of the world, which would have been right there. Is that a good visualization? Does this? So if I move this, this thing can move independently. But if I move this one, you get both. And so if I like scale this, it also will, so you'll notice that it also will scale the distance between them. So like as I'm scaling this, the cone's translation is also changing with the same scale factor as how big I'm making the box. That's because of the TRS order. Does that make sense? Does everyone see how this is working? Okay. All right, so yeah, that's the way transformations work. And yeah, Trung, do you want to take over?
You want me to use the second computer?
Yeah, if the slides are updated on Google, you can just use this one.
Do you also have Unreal on that computer?
I can switch over to Windows, yeah,
Oh,
because I don't have it on Mac.
okay, yeah, maybe, yeah.
Or you can use that one, either one.
Yeah, just use.
Okay, if you want to do the slides on here, it'll still present to YouTube, so maybe better that way. Then you can toggle it for Unreal.
I'll just use the computer.
Okay. Okay, so this part of the lecture won't be on the YouTube recording, unfortunately, because I'm trying to.
Do you want? Oh,
That's okay.
Okay.
You guys, so if you're here, take advantage of it. If you're not, sorry.